Hello, in today's lesson we're going to be learning section 12.2, which is about vectors. Vectors are really important in physics particularly, but it's used in other kinds of science and engineering all the time. And some of you may have learned it from other classes, others may be seeing it for the first time. But again, they're very useful in the real world, and we're going to be learning the basics of them in this section. Okay, so what is a vector, first of all? Well, a vector consists of 2 points. And the first point is called the initial point. And the second point is called the terminal point. Okay, and then when you're drawing a vector, when you're graphing a vector, you start at the initial point and you draw a line segment to the terminal point, and then your arrow, you actually draw an arrow that points from the initial point towards the terminal point. And that actually makes a vector. So a vector actually is a line segment, but it has a direction. Okay? And then, for example, here we could call the initial point A and the terminal point B. Then we would say this is a vector, and we write, for this vector, we write vector AB. And then we write an arrow over it, so a line segment and an arrow over it. Okay, so a vector has an initial point, a terminal point, and it's really just a line segment and then an arrow pointing one direction on the line segment. And vectors can be either two-dimensional or three-dimensional, but they're actually really pretty straightforward to understand in both cases. All right, and when you have a vector, it's kind of nice to see an example. So let me do an actual example of a vector. So for example, graph the two-dimensional vector. Graph the two-dimensional vector. And we're going to do the two-dimensional vector, I'm calling this vector v, equals 1, comma, negative 2. Now, we were calling the vector up there the vector AB. Here I'm just calling the vector v, and we want to graph it. So how do you graph this? Well, this is what's called a component form. This right here is component form. Where we have the 1, comma, negative 2. And what we're going to be doing with that is when you graph it, you have your initial point start at the origin. That's what the component form means. So initial point is the origin. So it's 0, comma, 0. So what's the graph going to look like? Well, I'm not so great at graphing on here, but I think we can get the basic idea down. So you draw your x and your y axis because it's two-dimensional. So there's your x-axis, there's your y-axis. And remember, two-dimensional means x and y. So it's only two dimensions because it has only two axes, the x-axis and the y-axis. And if I want to graph 1, comma, negative 2, I actually just plot the point 1, comma, negative 2. So x is 1, and then y is negative 2. And then I plot my point right there. And that point that I plotted there, 1 comma negative 2, that's actually going to be the terminal point of my vector v. Okay, so I have my initial point at the origin, and then my terminal point is going to be 1 comma negative 2. So the initial point is always the origin when they have a component form vector like this. It's also called a position vector in some other books. But the initial point is 0 comma 0, and then the terminal point is 1 comma negative 2. Okay? And when I say component form, that's also called a position vector. And the reason it's called a position vector is because a position vector always has the initial point positioned at the origin. So it's always positioned at 0 comma 0. Okay? So that's the basics of a two-dimensional vector. And then keep in mind you can also graph a three-dimensional vector. Okay, so three-dimensional vector is going to be graphed in a similar way. I'll do a quick example of that. You're not actually going to have to sketch graphs on your homework, but it's good to see them anyway. Okay, so let's do a new example. Graph the three-dimensional vector. Here I'm just going to write 3D as an abbreviation for three-dimensional. Okay, so we want to graph the 3D vector, and I'm going to call this vector u. Okay, it's going to be vector u, and then we're going to write this as a component vector. So I write angle braces here. That's what those are called, the little arrow. And then I'll pick some numbers. So let's do 1 comma 2 comma negative 1. Okay, so for the last example that we did, because it was two-dimensional, this was x comma y. So 1 comma negative 2 is actually the terminal point of our position vector. Well, here, because it's a 3D vector, in this example, instead of being x comma y, we're actually going to have three coordinates. We're going to have x comma y comma z. Okay, that's what 3D means. 3D means you have three components. But this is still a position vector, and this is in component form. So what's the initial point going to be? Well, when it's written as a position vector or in component form, the initial point is always the origin. But because this is a 3D vector, the initial point is going to be 0 comma 0 comma 0. All right, because there's three dimensions. And then can anyone guess what the terminal point is going to be? Well, if this were a live class, I would ask you. But you're probably able to think in your head, well, the terminal point is probably just going to be 1 comma 2 comma negative 1. And that's correct. So the nice thing about these position vectors, and the reason we're learning about them first, is they always start at 0, 0 or 0, 0, 0, and then they always end at the point that they gave you. So this is going to end at 1 comma 2 comma negative 1 for your terminal point. Now to sketch this, different books draw it different ways. But the way I like to draw our coordinate system in 3D is I let the z-axis actually be the vertical axis. And I think this is how our book does it too. So the z-axis is going to be the vertical axis. And then the axis coming out at us is going to be actually the x-axis. So that's x, that's y, and then the vertical axis is z. Okay, so if I want to do a sketch of this vector, we're going to start at 0, 0, 0, so that's at the origin. That's our initial point. Okay, and then our terminal point is going to be, well, x is 1, y is 2, and z is negative 1. So I'm going to go 1 out on the x-axis, that's right there. And then on the y-axis, I'm going to be going 2 to the right. So that's going to bring me to right here. That's going to be right there. And then on the z-axis, I want to go down to negative 1. So that's going to bring me down negative 1 to here. So my vector is going to be right about there. And obviously 3D vectors are hard to draw, but you're not going to actually have to draw in this class. If you do have any graphing problems, you'll just be looking at graphs, and then they'll be asking you questions about those graphs. So you just have to have an understanding. You don't have to be an artist or anything. Because I certainly am not an artist, as you can see. But that's our vector, and that's vector u. Okay? So that's at 1 on the x-axis, 2 on the y-axis, and then negative 1 on the z-axis. And I think I forgot to label the other one on the picture. Yeah, you can label them on the picture if you want. This other vector that we wrote here, this was vector v. Okay, so that's the basics of graphing vectors. We're not going to be doing much of that in your homework, but it's important to understand what vectors actually are before we start doing math with them. Okay, so we've talked about these vectors, and we know that they have a little line segment with a direction. And you might be wondering, well, is there any way to talk about the length of the line segment? And is there a way to find the length of that line segment, you know, from there to there? And the answer is yes. You can actually just use the distance formula. And there's a special name for the length of that line segment, or the length of a vector. So that's what we're learning about next. So the length of a vector, the length of a vector, and here we're going to call it vector v, which is going to equal capital AB. Okay, so it's going to start at point A and end at point B. It's written actually, most books write it as what looks like an absolute value. So absolute value. So it looks like absolute value because it has the vertical bars on either side. This length you can actually find using the distance formula. So we write this as, it's actually going to be the square root of the difference of the squares. So it's going to be the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And if it was just two-dimensional, then it would only have those first two terms. But if it's three-dimensional, if it's a three-dimensional vector, then it's going to have one more term, which is going to be the quantity z2 minus z1 quantity squared. And here we're assuming that point A, so point A is equal to x1 comma y1 comma z1, and point B is equal to x2 comma y2 comma z2. Okay, so that's the length of a vector v equals AB, going from point x1 comma y1 z1 and going to x2 comma y2 comma z2. And obviously you can do this for a two-dimensional vector as well. It just wouldn't be having this third term here. So it wouldn't have anything involving z. So if it were a two-dimensional vector, we would just have these first two terms, the x2 minus x1 squared and the y2 minus y1 squared, but you wouldn't have this one. Okay, so examples are probably the best way to learn about the length of a vector. Okay, so let's see an example. Example, determine the length of each vector. Determine the length of each vector. Okay, and for problem number 1, we're going to have the vector, and our vector is going to be, I'm going to call it PQ, where the initial point P equals 1, 2, and the terminal point Q equals -2, +3. Okay, so we want to find the length of PQ, where the initial point is capital P equals 1, 2, and capital Q equals -2, 3. So how do we do that? Well, we actually just use the distance formula. Notice here, this is only a two-dimensional vector, so it's going to be this formula, but we're not going to have the z. So it's actually just going to be this first part of the formula. So you can label things here. Our initial point is P, so that's going to be our x1, y1. And then our terminal point is Q, so that's going to be our x2, y2. And notice this is a 2D vector. This is 2D, because it only has two components. Okay, and then we plug into the formula. So the length of PQ, the length of vector PQ, is going to equal the square root of x2 minus x1, so that's going to be -2 minus 1, quantity squared, plus y2 minus y1, so that's going to be the quantity 3 minus 2, quantity squared. All right, and because it's a 2D vector, we don't need to have a z2 minus z1. So that's our whole formula there. Okay, and then we simplify this using PEMDAS. So first we do our parentheses. So on the inside here we have -2 minus 1 is -3. So we have the quantity -3 quantity squared. Don't forget you still have a square root here. Okay, and then over here 3 minus 2 is going to be 1 squared. So on the inside here you should have -3 quantity squared plus 1 squared. Now remember that -3 quantity squared, because you're squaring a negative, the minus cancels out and becomes positive. Okay, so we're actually just going to have 3 squared is +9. So we have 9 plus 1 squared is 1. So that's going to give us the square root of 10. Okay, and what's the name of the thing that we just found there? That's actually the length of PQ. And there's other names for the length of PQ that most people call it the length. But there are other names like magnitude is another name for length. Some books even call it the norm of a vector. But this is the length of vector PQ. Okay. So since I talked about it, why don't I write it down before we do more examples? Okay. So other names for length, other names for the length of a vector. include, I mean, this might not be all of them, but these are the ones that I can think of right now. Include magnitude. Okay, the reason magnitude is the same as length, as it's the idea of how long it is or how strong a force is. That's the magnitude of the force. So other names for the length of a vector include magnitude, norm. Norm is another name. And then there's probably another one that I can't think of it right off the top of my head, but some people call it distance, I guess. That one's pretty rare, but so distance from terminal point, from initial point to terminal point. I guess it doesn't really matter, but people usually start with the initial point. So distance from initial point to terminal point. So I'll put that one in parentheses. It's usually either length or magnitude, and some books call it the norm of the vector. Okay? And it can be written. It can be written the way we wrote it, which was with absolute value. So absolute value of V, or absolute value of PQ like we did there. But you can also write it with 2 vertical bars. I don't think our book ever does that, but some other books do. So it kind of looks like a double absolute value when you look at it. So something like that. So these two things mean the same thing. Okay. So those both mean the same thing. Okay, so I just want to clear that up in case you're taking a physics class or some other class that has vectors, and you might see the double vertical lines that looks like a double absolute value, but they actually mean the same thing. Okay, so we've done the magnitude or length of a 2-dimensional vector, and then real quick I want to do the length of a 3-dimensional vector. So part 2 of our example. And this time, why don't we go ahead and work, instead of with an initial point and a terminal point, we're actually going to work with just a vector that's written in component form or as a position vector. And this one's going to be 3-dimensional. So let me pick some numbers here. Let's do 2, -5, +1. 2, -5, +1. So notice again here, when you have this special notation where it looks like it has a less than sign on the left side and a greater than sign on the right hand side, this is called a position vector. Position vector. Or our book calls it component form. Component form. It's called a position vector because the initial point is 0, 0, 0. So it's positioned right at the origin. Okay, so position vector starts at 0, 0, 0. That's the initial point. Okay, so that's the idea with a position vector. We already talked about that earlier, though, so that might be good enough for you to understand that. And so the question is, how do you find the length of this vector? How do I find the length of vector v? Well, the length, I'm going to write with absolute value, the absolute value symbol. That's what our book does. The length of vector v is going to be the square root of the quantity x2 minus x1 quantity squared plus the quantity y2 minus y1 quantity squared plus the quantity z2 minus z1 quantity squared. And we take the square root of that whole thing. So then once you get comfortable with these, you're going to realize that it's actually a lot easier to find the length of a vector when it's already written as a position vector. Because what does that mean? Well, that's the 0, 0, 0. That's actually going to be our x1, y1, and z1. Okay, that's our initial point. x1, y1, and z1. They're all going to be 0. So when I want to find the length of a position vector, it's just going to end up that I add up the squares of all these numbers in the position vector, and then I take the square root at the end. Okay, so each one of these is 0, 0, 0. And then the x2, y2, z2, that's going to be the point that they gave us. So x2 is going to be 2, y2 is going to be negative 5, and z2 is going to be positive 1. Okay? So if I plug all that in here, I'm actually going to get the square root of x2, which is 2 squared, plus y2, which is negative 5 quantity squared. And then I'm going to have plus z2, which we said was 1 squared. And notice I put parentheses around the negative 5 because it's negative, and I actually want the square. I actually want the square to apply to the negative as well as the 5. Okay, so so with that, it's actually a lot easier to find the length of a position vector. And again, a position vector starts at 0, 0, 0. So how do we simplify this? Well, 2 squared is 4. And then negative 5 quantity squared, the minuses cancel when you're squaring. So that gives us 25. So we have 4 plus 25 plus 1 squared is 1. So after we do all this, we have 4 plus 25 is 29 plus 1 is 30. So we actually get the square root of 30. And then my question for you is, how do you simplify a square root, and can we simplify this one? Well, if you don't remember, all you do is you try to factor it. So if you think of factoring 30, it factors as 15 times 2, which is 5 times 3 times 2. Well, you can't take the square root of any of those factors, so that means you just leave it as root 30. So here the length of v is just going to be left as root 30. Okay? So that's not so bad. Okay, cool. So the next topic I wanted to talk about is when you have vectors, we talked about them as being directed line segments in space. You can actually add and subtract vectors, and you can also multiply vectors times numbers, which are called scalars. So that's the next thing we're going to learn about. So we're going to start with what's called scalar multiplication. Scalar multiplication. The basic idea here is if you have a vector, say you have vector v. Let's say we have vector v has a position vector form of v1, comma v2, comma v3. Keep in mind those are going to be numbers in an actual problem. They just call them v1, v2, v3 to represent the components of your component form? Well, if that's your vector v, and then k is a real number. A real number. Remember, a real number, it could be like any number, like 2 or 7 or negative 3.2, anything like that. Scalar multiplication is going to be k, which is your scalar, or the real number, times your vector v. So k times v is actually going to give us k times the position vector, which is v1, comma, v2, comma, v3. And what do you do with the k? Well, k is just a real number, and you're actually able to just distribute it. Distribute the k. Okay, so we distribute. And that's going to give us a new vector, and this new vector is going to be k v1, comma, k v2, comma, k v3. Okay? And that is scalar multiplication. And it'll probably be easier for you to understand when we do an actual example. But keep in mind that k is a real number, and if it's a real number, that's going to be called a scalar. So k is actually a scalar. A scalar is any real number. So in particular, we call it a scalar because it's not a vector. It doesn't have components. It's just a single number, whereas a vector has different components. It has the x-coordinate, the y-coordinate, and then the z-coordinate if it's 3D. Okay? So that's scalar multiplication. And then let's see an example of that. That'll probably be helpful. Okay, so example. Find 2v and negative 3v. All right, and here they're telling us where v is the vector equal to component form 1, comma, negative 2, comma, 0. Okay? So what kind of vector is this? Is this 2D or 3D? Well, we know it's 3D because it actually has 3 components, and that's our x, y, and our z. And 2 and negative 3 are called scalars because they're just real numbers. So let's start with 2v. It's actually pretty simple. All you do is you write down 2v, and then you write out vector v in its component form or as a position vector. So it's going to be 2 times 1, comma, negative 2, comma, 0. And then you just distribute the 2 to each term, or to each component rather. Okay, so once you distribute the 2, you're just going to be multiplying. So that's going to be 2 times 1 is 2, 2 times negative 2 is negative 4, and 2 times 0 is 0. So that's going to give us the position vector 2, comma, negative 4, comma, 0. And that's actually our answer for the 2v. So most people find scalar multiplication to be pretty straightforward. It's not so bad. And then they also wanted us to find negative 3v. So we're going to be doing the same idea. It's just here we're going to be distributing a negative 3. So negative 3v is going to be negative 3 times 1, comma, negative 2, comma, 0. And that's, we're going to be distributing the minus as well as the 3. So that's going to change the sign of each of those components. So for the first component, we're going to have negative 3 times 1, which is negative 3. For the second component, negative 3 times negative 2, which is positive 6. And for the third component, negative 3 times 0 is 0. Okay, so for our negative 3v, we get the position vector negative 3, 6, 0. Okay? And what does scalar multiplication mean when you look at it in space? Well, the basic idea of the graph of scalar multiplication is if you have a vector v, it's going to be a line segment with a direction. If this is vector v, well, what does it look like if you multiply it times 2? Well, let me do that in a different color. If you multiply a vector times 2, it's going to have the same direction, but twice the length. So that would be 2v. So this whole thing here would be 2v. And then if you multiply it times negative 1, for example, or in our case, negative 3. Oh, my kitty's here. Say hi to the camera, Max. Hi to the camera. Okay. So if we take a look at negative 3v, because it's negative, it's going to be pointing in the opposite direction. And then the 3 is actually going to make it 3 times as long. 1, 2, 3. So it'll be like way over here. So this would be a sketch of negative 3v. And if I were more of an artist, you would believe that these are all on the same line, but it's hard for me to draw on here. Okay? So that's the basic idea with scalar multiplication. I didn't actually do a full graph because you're not going to have to graph in your homework, so I didn't want to spend too much more time on it. And then you can also add vectors, add or subtract vectors. Okay, so let's talk about that next. So vector addition is what it's called. And the basic idea here is to add vectors, all you do is you add the components. You add the components. So remember, the components are the x-coordinate, the y-coordinate, and then the z-coordinate if it's 3D. If it's a three-dimensional vector. So to add vectors, you add the components. And so what is that going to look like in the graph? Well, just for a sketch of the graph, before we actually do a problem, if you have vector u somewhere like this, we'll call this vector u in red. And then we have another vector v. I'm going to do that vector v in blue. That'll be right here. So this is vector v in blue. And then what does it mean if we add these two vectors? Well, if you put them head to tail like this, they call the head the arrow and the tail the component without the arrow. Adding the vectors means it's just going to be this vector right here. So it's almost like you form a triangle out of the vectors. So this black vector that I'm drawing here, this is going to be u plus v. That's u plus v. And when you add the components, if you actually work all that out, you're going to see that this is exactly what the graph's going to look like. Okay? So that's vector addition. But when you're actually doing the problems, you're just going to be adding the components. Okay, which is pretty straightforward. So let's see an example of that. Okay, so example. Let vector v equal, let's have a three-dimensional vector, -2, +5, comma, positive 9. And then we're going to let vector u equal 0, comma, positive 3.5, comma 1. Okay. So vector v is negative 2, comma 5, comma 9, and vector u is going to be 0, comma 3.5, comma 1. And what we have to do here is we have to actually add the components. That's the first thing that we're going to be working on. But they're going to ask us some harder questions as well. So for part 1 of this example, let's find u plus v. U plus v. Okay. So u plus v, again, the picture looks like this bit up here, but you don't really have to worry about the picture when you're doing the math, because you're just going to be adding the components, which means for u, you have 0, and then for v, you have negative 2. So adding these components, we're going to get negative 2 plus 0. That's adding the first components. And then the second components, we get 5 plus 3.5. 5 plus 3.5. And then adding the last components, we get 9 plus 1. 9 plus 1. Okay? And then combining all these numbers, we get negative 2 plus 0 is negative 2. 5 plus 3.5 is going to give us 8.5. And then 9 plus 1 is going to give us 10. Okay, so there's our u plus v. Negative 2, comma 8.5, comma 10. Okay, and notice there I didn't actually have to sketch a graph. It wasn't necessary. All I did was add the x components, the y components, and the z components. Now you can actually combine scalar multiplication and vector addition together. So that's what we're going to see in the next example. Okay, so example number 2. This one's going to be a little bit harder, but most people don't find these that challenging once they get used to them. So let's find 3u minus 5v. Okay, we want to find 3u minus 5v. Alright, so what's that going to look like? Well, probably the best way to do this is to just write it all out. So we got, oh, there's Max again. See the tail? That's Max. That's my kitty. So 3u, what's that going to look like? Well, 3u is going to be 3 times 0, comma 3.5, comma 1. Okay, and then we have minus 5b is going to be minus 5 times negative 2, comma 5, comma 9. Minus 5 times negative 2, comma 5, comma 9. And by the way, in problem number 1, I accidentally added them in the wrong order. I actually did v plus u, but it didn't end up mattering because when you're adding, the order doesn't matter. But technically, in problem number 1 here, I should have had 0 plus negative 2 and 3.5 plus 5 and so forth. But because I was adding, I just didn't care about the order. That's why I wrote it in the wrong order and I got away with it. But here the order does matter for 3u minus 5v because u and v are different vectors and we're actually subtracting here. When you're adding, the order doesn't matter, but when you're subtracting, the order does matter. So we got 3 times vector u, 3 times vector u, minus 5 times vector v. Okay. And then what did I say you're supposed to do with scalar multiplication? Well, you actually want to just distribute the number. So here we're going to distribute the 3. for the first one. And then for the second vector, we're going to be distributing the negative 5. Remember, you don't just distribute the 5, you also distribute the negative, and you multiply each component. So what's this all going to look like? We're going to have, for the first vector, 3 times 0 is 0. 3 times 3.5 is going to give us 10.5. And then 3 times 1 is 3. So that's our 3u. And then for the minus 5v, since I'm distributing the negative 5, I'm just going to write a plus out front now, because I'm going to be distributing the negative 5 to each term. And then we've got negative 5 times negative 2 is positive 10. Negative 5 times positive 5 is negative 25. And then negative 5 times positive 9 is negative 45. Okay? And so with all that, we've distributed the scalars. So we've done the scalar multiplication. And now what we can do is I have it written as addition. So how do you add vectors? Well, you just add the components. So adding the components here, we get 0 plus 10, comma, 10.5 plus negative 25, comma, 3 plus negative 45. Okay? And you might be able to do those. You don't have to write them out like this, obviously. So you can do them on a calculator or in your head. They're not that bad. So we got 0 plus 10 is 10. And then 10.5 minus 25. What is that? That's going to give us negative 14.5, right? Negative 14.5. And then 3 plus negative 45 is going to give us negative 42. Okay? So the 3u minus 5v is 10, comma, negative 14.5, comma, negative 42. Alright, so before we go on to the next problem, I wanted to talk about a couple other things just to make sure you're solid. So we found 3u minus 5v. And then my question for you is, what's the name of this form that we wrote it in at the end? Well, the book calls it component form, but a lot of other books call it a position vector. So this thing that we found right here at the end, this is called, in our book they call it component form, but many other books would call it a component vector or a position vector. So position vector, because it's positioned at the origin. The initial point is actually 0, 0, 0. Alright, and I just wanted to do one more example of finding the length. So for number 3, let's actually find the length of this vector that we just determined. So let's find the length of 3u minus 5v. And in the book, sometimes they call length magnitude. So problem number 3 here is find the magnitude. Find the magnitude, which is the same as the length. I'll write length in parentheses. Find the magnitude of 3u minus 5v. Of 3u minus 5v. Okay, now the thing is, when you're doing a problem like this on your homework, you're not going to have to find 3u minus 5v again, because you just found it in problem number 2. So in problem number 2, we found that 3u minus 5v was 10, negative 14.5, comma, negative 42. Okay? So if we want to find the length of this vector, how do we write it? Well, in our book, we write it with the absolute value symbol. So it's going to be absolute value of 3u minus 5v. Absolute value of 3u minus 5v. And So here, we already figured out that that is actually 10, negative 14.5, negative 42. And remember, this is a position vector, so the initial point is just 0, 0, 0. So using the distance formula here, we're going to have the square root of 10 squared plus the quantity negative 14.5 quantity squared plus the quantity negative 42 quantity squared. Now with this one, we're probably going to need a calculator. If you have a calculator of some sort, you can use it. Otherwise, you can use the calculator in your phone. Or since you're going to probably be on a computer, you can just look up a calculator on your computer. So for example, here my calculator is right there in the start menu. It's just called calculator. And then I can go ahead and figure out what negative 14.5 squared is. Okay, so for negative 14.5 squared, there's parentheses around it, so the minus is going to cancel out, so it's going to give us a positive. So we're just going to be doing 14.5, and then I click the x squared button to square it, and that gives me 210.25. Okay, so we got 210.25. So 210.25 here. Most of us should already know from our times tables that 10 squared is 10 times 10, which is 100. So you probably shouldn't need a calculator for that one. But we did need the calculator for the 14.5. And I'm also going to use a calculator for the negative 42 squared. So for the negative 42 squared, I'm going to clear my calculator with the C button. And then I'm going to do, well, I know that the minus cancels out when you're squaring. The minuses cancel out. So I'm just going to be doing 42 times 42. Or alternately, like we did the last one, I can do 42 and then the x squared button if your calculator has a square. Either way, you're going to get 1,764. Okay, so we're going to have plus 1,764. Okay, and then obviously to combine all this stuff, we're going to want to use a calculator again. So we're going to do 100 plus 210.25. So clear the calculator. 100 plus 210.25 plus 1764 gives us 2,074.25. 2,074.25. Okay, and we still have to take the square root of this. So again, that's something you probably want to do on a calculator. I don't think it's this ugly in your homework. It's just because I made up some numbers here. That's why the numbers are kind of bad. But if I do square root, you should see this button here on your calculator. Yours might not have the little 2 there, but you should have a check mark around x. That's a square root button. So I'm going to go ahead and press that. And that gave me 45.54. And I'm just going to round to 2 decimal places. So because the next digit is a 3, that's going to round to 45.54. So this is approximately equal to 45.54. Okay? All right. So that should be good there. All right. So we've seen lots of examples of position vectors or component form, and then magnitude and length. So we should be good there. And I wanted to show you a different kind of problem here. One of your homework problems is about finding a component form of a vector when they give you the initial point and the terminal point. Okay, so this is a new example. And this one is find the component form. Find the component form. Remember, component form is the same as a position vector of the vector PQ, of the vector PQ, where P is equal to the point 8, 6, and Q is equal to the point 9, -2. Okay? So this is just a little bit different flavor of problem from the other ones. So when we were finding the length, we subtracted and then we squared each component. Here, it's actually easier. All we do is subtract each component. So how do you do this? You just have to know something. So important note, vector PQ means vector Q minus vector P. Okay, vector Q minus vector P. That's what PQ means, because P is going to be your initial point and Q is going to be your terminal point. So when they write PQ and you want to find component form, you actually just subtract the first vector from the second vector. So Q minus P. Okay, so here, subtracting the components, we get PQ equals, well, the second component of, the first component of Q is 9, and the first component of P is 8. So we're going to get 9 minus 8, comma, the second component of Q is -2, and the second component of P is 6. So we're going to have -2 minus 6. Sorry, my cat is distracting me here. Max, come on, knock it out, buddy. Just playing with the blinds. Say hi to Max. The most fun part of math class is having this kitty here with me. Okay. Alright, so anyway, you're just subtracting Q minus P, and we get 9 minus 8, which is 1 for the first component, and then -2 minus 6 is -8 for the second component. So we have 1, -8, and that's actually the component form or the position vector of PQ. So I'll go ahead and box that. Okay, so that was just another important detail that you're going to need on your homework. Okay, so I'm just kind of going through your homework here, making sure you know how to do everything in your homework. So the next type of problem that you might have a challenge with is unit vectors. So let me talk about unit vectors. Okay. So there are lots of different types of unit vectors, but when they call it a unit vector, they mean that it's a vector whose length or magnitude is actually 1. Okay, so a unit vector is any vector. A unit vector is any vector, so it can be pointing in any direction, of length 1. So the magnitude or length of the vector is 1. Okay? And the most popular unit vectors, sometimes called the standard unit vectors, are going to be called I, J, and K. Okay, so the most common unit vectors are, people usually put a hat over them. So you have I hat, which is the vector 1, 0, 0. 1, 0, 0. And then you have j hat. It's called j hat because it has a little hat on top of it. It's kind of dorky how they call it that, but you can see it has a hat on top of it. J hat is going to be the vector 0, 1, 0. And then k hat is the vector 0, 0, 1. Okay? Those are the most common unit vectors. And you can also convert any other vector into a unit vector by dividing by its magnitude. Okay? But before we do any of that, I wanted to show you an example of a problem where we write it in terms of unit vectors. Okay, so this is an important bit of information before we start the problem. Any vector in component form can be written as, well, if v is your vector, so if you have v equals, in component form, that's v1, v2, v3, you can actually rewrite this as v1 times I hat plus v2 times j hat plus v3 times k hat. And remember, those represent unit vectors. And the reason this works is a little bit complicated, but you can figure it out if you just multiply out the components. Because if you multiply your v1 times I hat, that's just going to give you your first component here. And then if you do v2 times j hat, that's going to give you your second component right there. And then v3 times k hat is going to give you your third component right there. So it actually does work out. But when you're doing it, it's very easy because it's just in the exact order that it's written for your component form. So your position vector is just going to be v1, v2, v3. Or you can write it as v1i plus v2j plus v3k. And these mean exactly the same thing. So it's two different ways of writing the same thing. Okay, so let's see an example, a quick example of this. Okay, so example, express the vector, and here they're calling the vector p1, p2, in the form v equals v1i plus v2j plus v3k. And by the way, in our book, they don't have the little hats. They actually just make the I, the j, and the k bold. But when people are writing on paper, they like to put the hat on it because you can't really make what you're writing down bold. So the hat means that it's bold. Okay. So and here for our vector p1, p2, they give us some information. They say that where p1 is the point, 2, -4, -1, and P2 is the point 7, 1, 6. Okay? So remember, before we can write in this form v1i plus v2j plus v3k, we actually have to subtract here. So remember that p1, p2 means p2 minus p1. So P1, P2 means vector P2 minus vector P1. In other words, we're just going to be subtracting the first point from the second point, and that will give us our component vector or our position vector. Okay. So what's that going to be? We're going to get P1, P2 equals, subtracting, we're going to have 7 minus 2, 7 minus 2, comma, 1 minus negative 4, comma, 6 minus negative 1. Okay, so that's just subtracting P2 minus P1, subtracting the components. Okay, and then we can simplify this a bit. So 7 minus 2 is 5. 1 plus 4 is 5. And then 6 plus 1 is 7. So we should have 5, 5, 7. And then where do we go with this? Well, remember in the original problem, they didn't just want, oops, sorry, my thing's messing up. They didn't just want the position vector. They actually wanted it in the form v1i plus v2j plus v3k. So all we have to do at the end here is write it as 5i hat plus 5j hat plus 7k hat. And then I'll box that. That's going to be our answer. Okay, and on my math lab, it might not have a little hat, but it'll just have the unit vector in bold there. So it'll just be bold I, bold J, and bold K. Okay? Alright, so the next thing I wanted to talk about is a special kind of unit vector. And this is called the direction vector. The direction is a unit vector pointing in the direction of your vector. The direction is a unit vector pointing in the direction of vector v. Okay? Or they can call it the direction of v. Sometimes they'll just say the direction, other times they'll say the direction of vector v. So, aka the direction of v. Two different names for the same thing. Okay? Now, how do you find the direction? It sounds like it might be hard to find, but it's actually pretty simple to determine. So, the direction of v is, we'll call it vector u, because it's a unit vector, and it's u equals vector v divided by the length of vector v. Vector v divided by its length. That's the direction of v. So that's a unit vector pointing in the direction of vector v. And when you're dividing by its length, because the length of v, say the length of v is 5, well, you're dividing by its length, which is also 5. After you end up doing that, the new length ends up being 1, and that makes it a unit vector. But because you're just dividing by the length, you're not changing the direction of the original vector. Okay? So it's helpful, particularly in physics. In physics, many times you want to express a vector as a product of its length, which we already know how to find, and its direction. So let's see an example. So example, express the vector as a product. Remember, product means multiply. As a product of its length and direction. So product of its length and direction. All right, so the original vector they're giving us here, they're not giving it a name. I'm going to call it vector v, though. We're going to call this vector v, and this is given to us as negative 12 I hat plus 6 j hat minus 12 k hat. Remember, on my math lab, it won't have the hats. It'll be in bold. But when you're writing on paper, you want it to have a hat, so you know that it's a vector. Okay, so first of all, what I'm going to do here is I'm going to rewrite as a component, in component form, or as a position vector. So this is the same as the vector with components negative 12, comma 6, comma negative 12. And then they want us to write it as a product of its length and its direction. So first we're going to find the length, and then we're going to find the direction, and then we'll write it as a product of those. Okay, so the length here is going to be the magnitude of vector v, so absolute value of vector v. And remember, because this is a position vector, the initial point is 0, 0, 0. So this is just going to be the square root of the sum of the squares. So this is going to be the square root of negative 12 squared plus 6 squared plus negative 12 squared. Okay, that's going to give us the length. And remember, when you're squaring a negative, it becomes a positive, so we can cross out those negatives. So what's that going to give us? Well, 12 squared is 144. 6 squared is 36. And then this 12 squared over here is also 144. Okay? And then let's see. If you can't do this in your head, you can do it on a calculator. It's not that difficult, but still. It's probably easier to just type it in. So 144 plus 36 plus 144 gives us 324. Okay, so the length is the square root of 324. And let's see if that simplifies on the calculator. Press the square root button. The square root of 324 is actually 18. So I press this button right here, little square root button. So the square root of 324 is 18. So that's the length of our vector. Our vector is length 18. Okay? So, but we want to express the vector as a product of its length and its direction. Okay, so let me scroll down here. We found the length. How do we find the direction? Well, the direction, we just said, is the same as vector v divided by its length. So vector v divided by the length of v. And since we know that the length of v here is 18, we just figured that out on the previous part. We don't have to calculate that part again. So we just need to write down vector v, which we said was negative 12, comma 6, comma negative 12. Negative 12, comma 6, comma negative 12. And we need to divide by its length. Well, its length is 18. Now we've talked about vector multiplication, where you multiply a constant to each component. Well, vector division works exactly the same. This is a scalar division. So we just divide each component by 18 and simplify. So just as if we were multiplying, but we're dividing in this case. So think of it as distributing the 18 to each denominator. So the direction here is going to be, the first component is going to be negative 12 over 18. Second component is going to be 6 over 18. And the third component is going to be negative 12 over 18. Okay, and then remember with fractions you can simplify them with some calculators, but these are pretty easy. So you just divide the top and the bottom by the same number to simplify it. So for this first fraction we divide the top and the bottom by 6. And we get 12 divided by 6 is 2, so we get negative 2 over, well, 18 divided by 6 is 3. So that's going to be negative 2/3. And then we do the same thing for the other components. For the second component, 6 divided by 6 is 1, and 18 divided by 6 is 3, so we get 1/3. And then for the third component, it's the same as the first component, so that's also going to be negative 2/3. Okay? All right, so that's actually the direction that we figured out there. So that is direction. That's the direction of vector v. But remember, in the instructions, they didn't ask us to find the length and the direction. They actually asked us to express the vector as a product of its length and direction. And remember that product just means multiply. Okay, so product means multiply. Okay, so if we go back down here, we said the length was 18, and the direction is this vector here. So we express vector, oops, wrong color. We express vector v as a product of its length, so its length times its direction. And I probably shouldn't use an x there, because that can get confusing. So instead I'm going to use just a dot. Okay, so length times direction. Well, we said the length was 18, and then we just figured out the direction is negative 2/3, comma 1/3, comma negative 2/3. Okay, and they want us to express our answer in terms of unit vectors. So at the very end here, I'm going to rewrite it as 18 times parentheses, negative 2/3 I hat, plus 1/3 j hat, minus 2/3 k hat. Alright, and the reason we're writing it that way is they want us to express vector v as a product of its length, which was 18, and then its direction, which is the vector v divided by v. Okay, so I'm going to go ahead and box this. This is how they want you to write your answer. And keep in mind here that this is really important in physics. We're not doing a lot of applications in this class, but we will be doing some at some point, probably in your discussion boards. But these are really important in physics because so many things in the real world can be expressed as vectors. Because if you think about it, for example, the speed of an object in space, it has what's called a velocity vector, which actually has a magnitude, which would be how fast the object is moving, and then it has a direction, well, which direction the object is moving. So that right there, the speed of an object plus its direction is called the velocity, and that's a vector. And then you also have position vectors, acceleration vectors, force vectors, and so many other kinds of vectors. It's very, very common in physics and very useful for engineers and people applying math to the real world. All right, And then for your homework from this section, it's quite a long homework in some ways, but not if you know what you're doing. There's one more type of problem that we haven't talked about, which is midpoint. Surprisingly, even though this is later in the section, this is actually a lot easier. Okay, so we'll do a quick example. You're going to find that you just use a pretty simple formula here, though. So example, find the midpoint. Find the midpoint of the line segment. Find the midpoint of the line segment P1, P2, where P1 is actually 7, 6, 5, and P2 is the point 6, 7, 6. Now the idea with a midpoint, I don't really want to graph it because there's only 2 problems in this section that involve this, but the idea with the midpoint is it's halfway between the starting point and the ending point. So if you wanted to know what's halfway between the initial point and the terminal point of your vector, you can find the midpoint. It's actually very straightforward to find. You just use the formula. So let me write down the formula. So the formula is M equals parentheses x1 plus x2 divided by 2, comma y1 plus y2 divided by 2, comma z1 plus z2 divided by 2. Okay, so basically all you do is you add each component and you divide by 2. And here you don't even have to do anything with a vector because they give you the initial point and the terminal point. So you're going to be actually just be adding the components and then dividing by 2. So here for our midpoint, we're calling it M. We have x1 plus x2, so that's going to be 7 plus 6 over 2. y1 plus y2 is going to be 6 plus 7 over 2. And then z1 plus z2 is going to be 5 plus 6 over 2. Alright, and then either with a calculator or by hand, this is not so bad. 7 plus 6 is going to be 13. So we have 13 halves, comma 6 plus 7 is also 13. So 13 halves, comma 5 plus 6 is 11. So that gives us 11 halves. Okay? And so that's actually your midpoint. And those fractions are already simplified, so we don't have to do anything there. So that right there is the midpoint. Midpoint of the line segment P1, P2. And keep in mind you can use this for a vector because remember a vector is actually a line segment but it has an arrow pointing one direction. Even so, it's still a line segment. So you can find the midpoint of a line segment and that's the midpoint of that same vector. Okay, so that's pretty cool and it's pretty easy to use.